The inequality symbols are used when we need to make comparisons between two quantities. Is one quantity greater than another? And we accomplish that with real numbers, which lie on the real number line. And the easiest explanation for how to define less than or greater than is simply which one falls to the left or which one falls to the right. So let me give you an example with the number line here. And now this number line, we would call it the real number line because it's a continuum which is unbounded on each end. So in other words, arrows means that it goes in both directions off to infinity. And there's a continuum there, which means that any point on this line can represent a unique number. So any decimal number you can come up with could theoretically fit somewhere on this line. So that makes it a real number line. And the real numbers are one-dimensional numbers. We talked about one-dimensional and two-dimensional numbers in a previous section when we talked about complex numbers. Because complex numbers are two-dimensional, and it becomes impossible to make any kind of real straightforward comparison of two numbers in size with complex numbers. You can sort of measure their distance from the origin in the complex plane, but two numbers which have the same distance to the origin, you can't say if one is greater than or less than the other, and you can't say they're equal to. So the notion of the inequality symbols that we're using is really only applicable to the real number system. All right, so we know that 1 is less than 2, of course, because it's smaller. Now that's just common sense experience. But how would you compare -1 to -2? And most students know that -1 is supposed to be greater than -2. I find most students can't give you a satisfactory explanation why. It just is. But there's a couple ways you could think of it. And for one thing, if you took -1 and subtract -2, then you get -1 plus 2. The two negatives cancel, and this becomes +1. So, and you expect that when you subtract a smaller number from a larger number, that you get a positive result, a positive answer. So that's one verification that -1 ought to be regarded as greater than -2, even though this 1 is smaller than that 2. Somehow things get switched when you go down in the negative range. I think the most straightforward explanation for why this ought to be true is because if you define less than and greater than in terms of position on the number line, then you can come up with a consistent rule. So here's the way it works. -1 is to the right of -2, so numbers to the right of another number are greater than. Numbers which are to the left of another number are less than. And so, you can look at something that looks sort of absurd like this. -1,000,000. How does it compare to 1? Well, this is a very large number. Very large number. But it's still less than 1. Now, to me, you wouldn't say it's smaller than 1. It's a very large number. But it is less than, and when you talk about less than, we're talking about position on the number line. So even though it's a very large number, it's less than 1 because of the position. Okay. Well, otherwise, it would obviously seem like this ought to be bigger than that number. Well, now this is going to lead us to a rule that's kind of interesting, and I realize you've probably seen this before. You may have forgotten some of the key things about inequalities that apply to algebra. And so if we compare 1 to 2, 1 of course is less than 2, but when you jump up here, suddenly we want to switch the inequality symbol around. Well, what happens is if you multiply by a negative number, So here I'll multiply both sides by -1. I'll multiply both sides by -1 up here. These negatives cancel, those negatives cancel, and I get 1 and 2. And so when I multiply by the negative number, the inequality symbol seems like it should reverse. So I want to go into a little deeper explanation of that, because it's really a geometric issue here. And you might think, well, where's the geometry of these numbers? Well, even numbers on a single dimensional number line have a geometry. So let me extend this line just a little bit more here so I can give you a few examples. All right, so let's take the numbers 1 and 2. 1 is less than 2. Okay, and here they are. 1's to the left of 2. If I add, let's say I add 2 to both sides. Okay, what happens? I get 3 is less than 4. So here's what I want you to see. When I added a positive number to this inequality, these two numbers shifted over to here. So we went from 1 and 2 over to 3, 4, and they remained the same amount apart, but it just shifted. If I were to do something similar, for example, let's go back to 1 is less than 2, and subtract 3 from both sides, then I get a -2 is less than -1, and so I have 1 and 2 shifted over to here. Everything shifted 3 units to the left. All right, so this shift is called a translation in geometry. So the geometric interpretation of addition and subtraction is translation. And when you translate, you don't flip the numbers around, you don't squeeze them together, pull them apart. You just slide without any kind of distortion or reflection. And so because we're just sliding without any change, then that preserves the distance between them, and also preserves the orientation of the numbers. So, you know, the left-hand number, which is less than, remains less than after adding or subtracting on an inequality. Now, multiplying and dividing is a little more interesting, and so let's take a look at that. If I have 1 is less than 2, and now I'm going to multiply this equation by 2, then I get 2 is less than 4. So what happened there? Well, we have 1 and 2, and when I multiply by 2, it became 2 and 4. So before they were 1 unit apart, now they're 2 units apart. I doubled the distance between them, and obviously because I multiplied both of them by 2. And so multiplying by a number changed the scale. In this case, it stretched it, made it larger. If I were to multiply instead by a half or divide by 2, I'll just keep the multiplying by a half. If I multiply by a half, both sides, then we would get 1/2 is less than 1. And look what happens there. They start off 1 unit apart, now they're closer together. So they came closer together, and so we might call that a compression. It was a compression. Now I want to take this to its logical end. Let's work with those compressions, and I'll go with 1 less than 2 again. Now this time I'm going to multiply by 1/100th. So now I have 1/100th is less than 2/100ths. And I think you'll agree those are pretty small numbers. They're very close to 0. So either multiplying by a very small number like 1/100th or dividing by 100 compress them very closely together. If I were to multiply by 0, what would happen? That would bring them right together at 0. And so as I multiply by smaller and smaller numbers, these two quantities get closer and closer as a compression. And I get to 0, they're right on, and if I go past 0 to the negative range, suddenly they've Does it make sense that they would reverse position? Well, they do. They reverse position once you start multiplying by a negative. So multiplying by a negative number causes what's called a reflection. When you reflect around something, you kind of do like this. I'm not sure how else to explain it, except attempt to demonstrate a reflection. But reflection will change the orientation around. That's what's happening when you multiply by a negative number. It's a reflection, geometric reflection. It changes the relative position of the numbers, and that forces us to change the inequality symbol from either less than over to greater than, or vice versa. So those are the type of operations we use in solving equations, and I want you to see the geometry of it. All right, well, let me solve a quick inequality, and we'll incorporate this some of this stuff I've been talking about here. All right, I'm going to solve 2x minus 7 is greater than or equal to 5x plus 2. Okay. Let's see. Now, the good news is that inequalities are solved just like equations. The steps are the same. But the difference is that we have to watch out for the circumstances under which we want to switch this inequality symbol. So I think my first step is to bring the x's together. Suppose I did it by subtracting 5x from both sides. All right, if I did that, then I would get negative 3x minus 7 is greater than or equal to 2. And then if we add 7 to both sides, then this cancels. I get negative 3x is greater than or equal to 9. Now, I subtracted the same number from both sides, and then I added a same number to both sides, and those were geometric translations. Those do not change the inequality symbol. At this point, however, to finish, I need to divide by negative 3, and dividing by negative 3 is the same as multiplying by a negative 1/3, and so it causes that reflection. By causing the reflection, it changes the orientation of the numbers, which means I have to change my inequality symbol. So the negative 3's cancel, and I get x is now less than or equal to negative 3. And there's my answer. All right, now keep that in your head, and I'm going to solve this problem a little bit differently. But again, multiplying or dividing by a number does not automatically switch the inequality. It's only when you do it with a negative number, multiply or divide by a negative, that you switch that. But there's one other situation in which we would want to change the inequality symbol. That I want to show you now. So we start back again with this problem. And suppose that in working this, I decided to subtract 2x instead. Okay, now it cancels on the left, so I get negative 7 greater than or equal to 3x plus 2. And now I'm going to divide by 2, subtract 2 from both sides. Negative 9 greater than or equal to 3x. At this point, we would divide by 3, wouldn't we? Now, dividing by a positive number does not produce a reflection. In this case, it produces a compression, but it does not reflect. In other words, we don't switch the inequality symbol when you divide by a positive. So I have negative 3 is greater than or equal to x. Now, I would encourage you to put x on the left side, because where we're headed next is we're going to graph these on number lines and also write the answer out in a different format called interval notation. But the graphing on the number line, people will mess it up frequently if they have x on the right side. So to make a case for that, put x on the left when you're done. If I do that here, switch sides, I have to switch the inequality symbol, because this reads x is less than or equal to negative 3 if you read right to left. So going left to right, I want x less than or equal to negative 3. which was the answer we had earlier, wasn't it? So three reasons to switch the inequality symbol. Multiplying by a negative, dividing by a negative, or switching sides, just swapping sides. That way you would change the inequality symbol.